Hello everyone, in this video we're going to be talking about the stability of carbocations, the radicals, and eventually the carboanions. Out of all three of those, carbocations are going to be the most common one, but that doesn't necessarily mean you don't see the radicals and carboanions at all. And the stability of carbocations is going to be dependent on three factors that we'll talk about those in a minute. But before we actually go in there, you want to make sure you know the terminology when something is primary, secondary, tertiary, methyl, allylic, and benzylic. So let me give you some examples. If I have only one carbon, or another way of saying I've got a methyl group, something like this, or I can have two carbons, something like that. So that's like an ethyl group, and then I can have a propyl group, and then let's talk about maybe in a tertiary butyl group right there. So if I suppose I got some sort of charge, like whether it's a positive charge, then it would be called a carbocation. If it's a electron, then it would be called a radical. If it's a negative charge, it would be called a carboanion. So if I have a charge or a radical or a negative or positive on this particular carbon, then it's just going to be called a methyl carbocation or methyl radical or a methyl carboanion, depending on what charge you have on that particular location. If I have the charge radical on this carbon, so this carbon has only one other carbon attached to it, so in that particularly case, it's going to be called in a primary. So you could have in a primary radical, carbocation, or carboanion, depending on what charge you got there. And then you have maybe charge, some sort of charge radical on this particular carbon here. Now you got two other carbons attached to it, one here and the second one here. So that's going to be the secondary. So I'm going to put the secondary there. So that could be in a secondary carbocation, radical, and carboanion again. And then eventually we could have a positive charge, negative charge, or electron on this particular carbon. So now this has three other carbons attached to it. So that's going to be called tertiary carbocation, radical, or carboanion. And then you can have another position where, let's say I got something like this. So if you have a double bond and one double bond away, you have this position right there. That position is going to be called an allylic position. So if you have a positive charge there, then it would be called an allylic carbocation. If it's a negative charge, then you call it allylic carboanion. If it's a radical there or electron there, then it's going to be called an allylic radical. Similarly, you can also have a benzylic position. So let's say this is going to be your benzene here. And off that benzene ring, you could have the first carbon, so that could have any sort of charge positive, then it would be benzylic carbocation. Negative makes it benzylic carboanion. And if you have electron, that would be making that a radical. So in addition to that, you can also have something called a vinyl position. So I'm going to go ahead and draw that out because you may see that as well. So vinyl is going to be where you have the charge on the double bonded carbon. So like this position, you can have a positive, a negative, or a radical on it. That would be called a vinyl position. So that could be in a vinyl carbocation, carboanion, and radical. So let's focus on carbocation first and talk about what makes the stable carbocation and what doesn't make the stable carbocation. So the first factor we're going to be looking at is hyperconjugation. So suppose I have a carbocation, so where I'm going to have a hydrogen attached to the carbon, and then there is a positive charge there, and versus I got a tertiary carbocation. So in a tertiary carbocation, I'm going to have other three methyl groups, or you could have, other R groups basically. It doesn't necessarily have to have only methyl groups. But when it's a tertiary carbocation, it's going to be more stable, and let's talk about why that's going to be more stable. So in either case, this carbon that's bearing the positive charge is going to be a sp2, and since it's an sp2, there is going to be one orbital that's going to be unhybridized. So there is going to be a p orbital that's going to be staying in there, that's going to be unhybridized. So I'll just go ahead and draw that in the dumbbell form. So same story in this particular case. There is a p orbital that's going to be unhybridized in the primary carbocation case as well. But you can have a hyperconjugation going on in a tertiary carbocation. That's because they're the carbon-hydrogen bond in the next methyl group. So if I draw that in the form of the orbital, like you can have a orbital that would look like this. So the sphere coming from the hydrogen because it's got one s orbital, and then you got this right there is going to be your sp3 hybrid orbital. This is going to be the 1s, and obviously this is going to be your unhybridized p orbital. So you got two electrons there, and they can so-called an hyperconjugate, or they can have a conjugation going on there, and as a result, that's going to make it a little bit more stable. So you have three hydrogens, and they're going to be doing the same thing. And in addition to that, you got these three methyl groups around this unhybridized p orbital that's gonna be on the carbon atom that's bearing a positive charge. So you're gonna have a multiple groups that can hyperconjugate onto that positively charged carbon, and as a result, that makes that carbon more stable because they have the electron donating tendency now. So that's one way of looking at it. And simply, when you're really looking at your carbocation, you usually say, okay, well, I'm going to have a carbocation that's going to be tertiary, but now I got all these electron donating groups around it, and that's going to make that positively charged center better in that case because all those electron donating groups would be donating in the electrons onto the positively charged group, and that makes it more stable. Now, how do they really donate in the electrons? They are donating in the electrons through a so-called hyperconjugation. So more electron donating groups you have, or more R groups you have around the positively charged carbon, the more stable it's going to be because it's going to be making more hyperconjugations there. So as a result, you don't really have any hyperconjugation in case of a methyl because you don't really have any adjacent carbon-hydrogen bond in that particular case. So there is no hyperconjugation. Okay, so as a result, if you have a tertiary carbocation, that's going to be the most stable out of all of those. So if I draw out something like this. That's going to be your most stable because it can hyperconjugate the most, followed by your secondary carbocation. That's going to be second most stable. And then your primary carbocations are going to be very less stable, and they are usually not even formed. And even when you're looking at your methyl carbocation, that's going to be even less stable than your primary carbocation. But when you're doing these reactions like SN1 and E1, for the most part, you're going to be looking at your secondaries and tertiaries carbocations to be made. Primary carbocations is less likely to be made because they are not stable enough by the hyperconjugation. So this is the order you're going to have. So tertiary and then secondary, primary, and then you got this methyl carbocation. So that's one way of looking at it. The second way of looking at it is resonance. So sometimes you could have resonance structures, or another way of saying you would have a pi bond close by. So you could have a positive charge at the allylic position. So this particular one would be your allylic carbocation. Now, why that's stable? Because it can resonate. So I can have this bond going in there. So when that bond goes in there, I can make another resonance structure. And since you have the delocation of this positive charge, that just makes it more stable. So that's why sometimes your carbocations that can have the resonances, they would be more stable. The same reason why your benzylic carbocation is going to be more stable because it can resonate the positive charge into the ring. So you got a positive charge there, and then obviously I'm not really going to draw all these resonance structures, but just get an idea that this can go down here, and you can have a bunch of resonance structures. So you may want to practice drawing those, and maybe I can draw just one of them. So if I just copy this down and erase a part of it. So let's see, this is how it's going to look like. Your double bond gets down here, and then your positive charge is here now, and you can just keep doing it. You can have this going down there, and you'll have new resonance structures. So the more resonance structure you have, the better you are. So this particular one is going to be your benzylic carbocation. Between the benzylic and allylic, your benzylic obviously is going to be more stable, but the general idea is more resonance structures you're going to have, the better you are in terms of the stability. So you could have another type of allylic where, I could have the one position shared by two double bonds in terms of being allylic. So that could also be more stable because you have more resonance structures in there. So in this case, I would say your benzylic is going to be more stable than your allylic carbocation. And how do you really determine that? It's just based on the number of resonance structures. The other thing you can look at is the lone pair next to the positive charge. I could possibly talk about, let's say, this carbocation right there, which seems like to be a secondary, versus this carbocation right there. But now I'm going to have a OH group attached to it. Now, this one is going to be more stable because there is a lone pair right next to that positive charge, which can actually draw, having a resonance structure. So that goes back to actually resonance structure, but just not having the pi bond involved in the resonance structure, but rather now you got this lone pair being involved in the resonance structure in this particular case. So you can have a resonance structure here, and that's what makes it more stable. So that's another thing you're going to be looking into. If you have a positive charge right next to a atom that has the lone pair of electrons, that particular lone pair of electron is going to be making that particular carbocation more stable. So this would be less stable. I mean, I can talk about maybe another example where I have both a positive charge there, but then I got maybe NH2 group there, and then a positive charge here. So since they're both kind of seems to be primary, but this second one has the nitrogen right next to it, so this nitrogen can, the lone pair can resonate in there to make another resonance structure, and since you can distribute that positive charge, that would make it more stable. So this one is going to be more stable. Okay, so how would I really compare maybe, tertiary carbocations with these allylic and benzylic? And um, it's not that easy. It's like comparing two different categories, two different effects there. And sometimes you may see conflicting informations when you go from one book to another book. But for the most part, the generic order and approximate order of your stability, your tertiary carbocation is still going to be winning over everything, even the benzylic carbocation. So I would still say your tertiary carbocation is going to be the most stable, followed by your benzylic carbocation. And like I said, you may have, different books kind of saying different things. They may have this benzylic and tertiary kind of either at the same stability level, or maybe some books have the benzylic over the tertiary carbocation. But it's you have a lot of hyperconjugation going on in the tertiary carbocation, especially when you have the CH3 groups attached to right next to the carbon that's bearing the positive charge, and that's what makes it really stable. So you're gonna have benzylic, and then after that you got this allylic. But turns out allylic and your secondary carbocations, they actually have the same stability level, and then followed by primary. And obviously your metals are going to be very less stable among all those. But sometimes you do have to look at multiple effects. Suppose if you have a condition where you have two effects being taking place. I can talk about an example where suppose I got this allylic carbocation, but then which one is going to be more stable? If I draw the resonance of that, and this comes down here, and after drawing the resonance, after coming that down here, where positive charge is going to relocate, now your positive charge is going to be down here. So now, which one is going to be more stable between those two carbocations? Well, it turns out this first one is allylic, and the second one is indeed allylic as well, but in addition to being allylic, it's also tertiary carbocation because this carbon now all of a sudden is attached to other two carbons, and you can say other three carbons because there's another carbon down there. So since this being in a tertiary, it's got two effects going on, and both of those two effects are going to be positive in terms of stability, stabilizing this carbocation. So as a result, this is going to be more stable. So sometimes you got to look at the additive effect, but a lot of times you're going to be comparing among just the secondary, tertiary, primary, and then you're going to be comparing separately with the allylic and benzylic. So this is how you're gonna be looking at your carbocation. They are a little bit tedious to understand in terms of the stability, and that's their approximate order, their general order in terms of stability trend. As far as your radicals go, they are gonna be easier to understand. Your radicals um, is going to be the benzylic radical is always going to be the most stable because of all the resonances it can make. I'm not really going to draw the resonances in this particular lecture, but I'll have a separate lecture where I'll draw the resonances. And then you have followed by this allylic radical. Oops, I should have made not this, but rather that's more stable. And then you can have the tertiary radical now. That's going to be less stable than your allylic. And then you got this secondary radical. And then you got this primary radical. And then you got this methyl radical. That's going to be your least stable out of all of those. When it comes to carboanion, that's like going back to the stability of conjugate bases. And remember, when you have a negative charge on the carbon, you want to make sure you can actually relocate that negative charge the better you are. In terms of relocating, obviously, you want to have your resonances. That's going to be the best to relocate your negative charge. So I can have these first two groups. I can have a benzylic carboanion, and I can have an allylic, not carbocation, rather, a carboanion, so negative charge there and a negative charge there. They are going to be more stable because they have more resonance structures. So remember comparing the benzylic with allylic, they are more stable because of the resonances. And then after that, who's going to be more stable? Well, it turns out it's going to be your CH3 carboanion or methyl carboanion. That's because you don't really want to have any extra electron donating groups right next to a negative charge. More electron donating groups you're going to have right next to a negative charge, the worse it's going to be. It's not going to be that stable in that case. So that's methyl is going to be more stable, followed by your primary carboanion, followed by your secondary carboanion, and then your tertiary carboanion is going to be the least stable in this case because it's got the most electron donating groups on them, and they're going to be donating in the electron to the carbon that's already electron rich. So you don't want to be doing that. So that's why that's going to be the least stable in that particular case. And this should be a relatively easier to understand because this kind of goes back to the stability of conjugate bases. And if you recall, if I go ahead and draw out something like suppose this, and then I got a double bonded carbon, and then I got a triple bonded carbon. So all these carboanions, so out of those three, who's going to be more stable? Well, I'll look at two different ways. If I look at acids, this one is going to be the ethyl, this one is going to be the ethane. All right, this one is going to be your ethane or alkene in this particular case. And then obviously this one is going to be your alkyne. The pKa of your alkanes is about 50 or more than 50, 50 to 60. The alkenes is about 44, and alkyne is going to be 25. So out of all of those, who's going to be most acidic? Well, this got to be the most acidic. And why that's going to be most acidic? Well, first, because it's got the low pKa, but the second, and probably the most important reason in terms of the stability of your conjugate base, this conjugate base that you have made, this carbon is going to be, you can say only sp, in that lone pair is going to be the closest in to the nucleus. In sp character, you're going to have 50% s and you're going to have 50% p. So that means you having more s character closer you're going to be to the nucleus. So this lone pair is actually going to be closer to the nucleus. and nucleus is the positive charge, so it's going to be hanging on to that negative charge better compared to the other guys. So here you're going to have an sp2, and here we're looking at sp3, least stable in that case, and this is going to be your most stable. So if you're comparing your vinyl carboanions versus your this acetylide where you have a triple bond and the negative charge on the carbon versus just a regular carbanion, remember your carbanion with the triple bond is going to be the most stable because of the percentage S character in there. The opposite can be said when we're looking at your carbocation. So which carbocation is going to be most stable? So suppose I got this one versus this one right there. So between those two, who's going to be more stable? Well, we can use the same analogy here. So remember, there's still one more hydrogen there, and there is going to be two hydrogens here, you can say. So this would have been sp, this would have been your sp2, because remember in the previous case you had the lone pairs, so those lone pairs counted in the hybrid orbitals, so that's why their hybridization were slightly different. But you can still use the same analogy there where this is going to be 50% s and 50% p, and then this is going to be 33% s, and then almost 67% roughly p. When we're looking at the first one, since you have more S character, this positive charge is going to be closer to the nucleus. Well, do you really want to have the positive charge closer to the nucleus? Well, the answer is no, because your nucleus is itself a positive charge, so it's going to be start repelling that positive charge, so that's going to be your most unstable. So that's why your vinyl carbocations are going to be the most unstable out of all of those, even more unstable than your metal carbocation. And this one is going to be more stable compared to the other one. So if I want to go back and, if I want to just kind of go ahead and put the vinyl carbocation somewhere, so I would put the vinyl carbocation even after your methyl group. So this is where vinyl carbocation will go. And then you can also say the phenyl after that. So phenyl means you will have a ring, and then you're going to have a positive charge right on the ring. So that's going to be even less unstable. So that's how you're going to be looking at them. If I want to look at this particular question here before we go, so what we're really going on here. So this is going to be your benzylic only. When I'm looking at this, this is benzylic. And I can probably say this is also going to be your tertiary carbocation because you got 1, 2, and 3. You can say it like that. And then this one is only going to be tertiary. So if I want to compare the stabilities, the second one has two effects going on. It's got the resonance and it's got the hyperconjugation effect. So that's going to be your most stable. So if I call this A, B, and C, then in terms of the stability, your B should be the most stable, followed by your C, because your hyperconjugation is still going to be taking over the benzylic especially when the benzylic is all by itself, and then followed by your A.